Tuesday, what do you think was this lattice theoretic view of how we think about clusterings? Do you have any thoughts about it? Sorry?
I have to think about it more.
You think about it, fair enough. Yeah. I mean, the point is that the basic idea, synopsis, was that the space of all partitions of a data set, or of an n item, right, forms this thing called a lattice. And you don't have to think of it as a lattice. You can just think of it as a collection of partitions. But by thinking of what is a lattice, giving it that extra structure, it gives you a principled way to compare clusters and measure distance between them in a way that you wouldn't ordinarily be able to do. So that's the point. A lot of these abstractions, all this idea of putting structure on a space is to give it a structure that is hopefully meaningful for the problem you want to solve. And there are other ways you could imagine putting structure on a space. For example, after class, I mentioned that you can construct a certain kind of topology from a lattice. That you could think about this topology, and people have done these things. But again, it all depends on whether it's effective in what you want. And here, the effectiveness comes from being able to measure distances. So that's the high-level synopsis of why we talked about lattice.
What do the Betty numbers say in that case?
You know what? I have no clue. It's an excellent question. There's a very nice set of notes, like a 100-page set of notes on basically four-set lattices. Four-sets and lattices.
Is it the IAS notes?
The proxy terms?
Yeah.
Yes, that one. You seen that one?
Yeah.
Ah.
I Googled it.
So there's the, I don't know if she talks about Betty numbers and that's in that notes, but that's the first thing that occurred to me. Like, so what does Betty 0 mean for this space?
Right.
Or 1 or 2? Yeah, I don't know the answer. But that's a good question. Okay, so today we'll be doing a bit of two different things. So we're going to be continuing to talk a little bit more about consensus clustering, especially about how you might try to do consensus when you don't have the nice structure we talked about from last time. And I'll review that in a second. And then we'll talk about another problem that comes in meta-clustering, which is called alternate clustering, finding alternate hypotheses to explain a data. Okay, and I mentioned that early on that we might want to do this, and I'll talk a little bit about how. These are not going to be as rigorous or as formal as some of the other algorithms we've seen, mainly because these are not as well-defined in the problem. So the main goal is setting up some kind of optimization and saying, wait, let's start to optimize this function. Right, so the algorithms are going to be less maybe satisfying. But there is a nice way to think about these things, and that's what I want to convey. And then finally, we'll talk about some attempts, and this is a good way to sort of end before spring break, some attempts to axiomatize what it means for something to be able to clustering or not. And any kind of axiomatization is necessarily somewhat controversial because you choose certain axioms or you don't. Suddenly you think, two parallel lines will never meet and the world changes, things like that. So we'll discuss these axiom systems for clustering and talk about whether they make sense or they don't make sense, what the pros and cons are, and so on and so forth. Okay. So if you remember from last time, we made this. We said that if we have a collection of clusters, so let's go back to consensus. You have a collection of clusterings. C1 up to Cn, let's say. And you want to find some kind of consensus answer. Right? So you want to find some answer that kind of reflects the average belief of what you have. And of course, since these are not points in a vector space, not directly anyway, you can't average them in a normal sense. You have to find some other way of doing an average. And as we've seen from lecture 1, I think, the natural analog to an average is to think of this functional way where you define some kind of distance function. And you say that C is equal to the arg min over all partitions in the space of partitions of the input, the distance, the sum of distances from Ci to P. Right? So you come up with some partition, you measure its distance to all of these things, add them up, and you find the thing that minimizes. It's like the one median. And so the problem of consensus then becomes the problem of, well, how do you define this distance? And then we talked about different ways of defining distances. One particular measure we came up with was what's called the RAND distance, or the distance induced by the RAND index, which basically measures the number of pairs of points whose clustering co-membership these two disagree on. So in other words, if in one clustering, so you take a pair of points x and y, if they belong to one cluster of C, but they belong to two clusters of P, then they differ, right? And so you just measure the difference. You could think of this as a Hamming distance. You can think of this gigantic n choose 2 long vector with a 1 for each pair if they're in the same cluster and a 0 if they're not. And you take two such vectors, one for each clustering, take the difference. That's what you're getting. And you can normalize it by n choose 2 if you want a number of things 0. So once you have this distance, you can say, okay, how do I find consensus under this distance function? And it turns out there's a very easy way to do that. That if you now construct a matrix where the rows are all the points, so it's 1 through n, and the columns are also all the points, And for each pair of points, right, what you put in there, Sij, is equal to the number of clusterings in which they are together minus the number of clusterings in which they are apart. So you have n clusterings, right? So each number is between m and minus n, right? That gives you a score here, and you get this matrix. And now you have a matrix consisting of pluses and minus values. And what you want to do now is cluster this matrix, cluster these objects. And as we've seen before, if you have a matrix of pluses and minuses, the first thing that should come to mind is correlation clustering, because that's what you use to cluster plus and minuses. So you can now say, okay, I want to find the max agreement clustering with respect to these weights. Right? So for every pair Sij, if you put them together, that's a profit, but if you put them apart, it's negative. And it turns out, miraculously, that the max agreement correlation clustering constructed from this matrix is exactly the thing that minimizes this. So you can get modulo your ability to solve this problem optimally, you can get an exact answer to the problem of consensus under the RAND distance. Okay, for that particular distance function, because that's where it kind of works out nicely. And so we have at least one example of how to compute a consensus clustering from a bunch of different clusterings using something we've already learned how to do before. So we don't need a brand new algorithm. Okay? So this is what we talked about last time. And that's where where we ended with this particular method. Any questions about what we did last time? Those of you who saw this before and are hopefully not too fuzzy about this. Okay. By the way, I saw the note on the forum about the notes, and I apologize for being late. The problem is that I'm trying to write the notes for the class, but they're not in a good enough form for them to put them up to read. This is my little scribblings here, and since Spring Break is coming up, since Spring Break is not really a break for anyone except you all, so I'm going to be busy sort of putting these notes together for the last couple of lectures in a reasonable form so that you can actually have them to read. That's my hope. Okay. So this method works if you wish to cluster using the RAND distance alone. Of course, in general, this may not be the case. You may not have this convenient relationship from a RAND distance to. For example, one of the other distance functions we talked about that uses the lattice structure is this information theoretic notion of distance, where we said the distance between two clusterings is equal to the entropy of the first plus the entropy of the second. Actually, maybe I flip this around. I should flip this around. Is the entropy of the first and the entropy of the second, right? And then twice the entropy of their split. Again, the lattice, this meant the clustering that could form, the biggest clustering, the highest one that could form either of these two by merge operations. So it's a split of these two things, right? So as the clustering gets split more, the entropy increases, so you get this function, and this distance is defined as this. And we talked about how you can show this in fact a metric for various reasons that I won't get into, which goes back into lattice theory and things like that. And so for this measure, for example, this would not work, right? There's no reason to believe that using this kind of sign matrix would give you an optimal solution for a consensus under this function. And so in general, if you have some other kind of function there, and there are others that people looked at, we would like something more generic to find consensus. Right? We don't want something that relies on this very specific form this way. And so it turns out, again, and this is where we get into the realm of heuristics. Right? There are many different heuristics you can now employ for trying to search for a solution. None of them are very pleasing, but they are what they are. And so the idea is that you construct some kind of hypergraph. So what you do is you think of, you construct this gigantic matrix. Okay? So you have one row for every point. Okay? And what you do is you list out the individual clusterings that you're thinking about. So let's say this is clustering number 1, clustering number 2, clustering number 3. C1, C2, C3. And within each, you have this matrix that sort of says, okay, I have cluster 1, it has point 1, 5, and 7. Cluster 2 has this, this, and this. Cluster 3 has this, this, and this, and this. And so this is, you have 1, 2, 3 clusters here. And again, you might have 1, 2, 3, 4 clusters here. And you have 1, 2, 3, 4, 5 clusters here, for example. So you build this gigantic matrix. Right? And you can think of this as a hypergraph. Yeah. So a hypergraph is a generalization of a graph where edges are now subsets of things and not single things. So you can think of this as one big hypergraph. And there are a number of heuristic methods that basically boil down to trying to cut this hypergraph into pieces so that you can do clustering. So what you basically want to do is you want to say that if 2 points are in the same, if a group of points are in the same cluster in one and the other in the other, you kind of split them up into pieces and you find some other pieces here. There's a number of heuristics that basically do a branch and bound search through the space. And again, I won't bore you with the details. I'll give you a link to the paper that talks about this. They're again heuristic methods. So if you have any other kind of function, you can try to search through the space of this hypergraph to find the appropriate things. All right. So another way to do this, which is similar to what we talked about here, was to try to use this information to build some kind of similarity structure. So you could build a similarity matrix the way we said and do consensus, right? So the basic procedure is you take clustering C1 to CK, you put them into some system, this outputs a similarity matrix, and then you cluster it, right? And so if you use a particular method based on correlation, you can use correlation clustering. If you use some other kind of similarity method, you might end up with something that uses spectral clustering, which is another way to deal with the matrix of correlations, and so on and so forth. So there are different heuristics that are based on saying, build some kind of similarity structure between points based on the number of clusterings in which they seem to show up together, and weight them appropriately, and then do some kind of clustering on the data. And again, how you do it is up to you. Except for this nice clean case we saw before, there aren't any examples where I can prove that this will give you something. All right. I should say that the problem of consensus actually did not come up from the sort of computer science, data mining, machine learning literature. It actually came up in biology. So, which also, by the way, is a place where a lot of the work on dendrograms came from. And the reason there, again, is that they do a lot of ensemble clustering because they have lots of problems where they don't really have a good sense of what the right clustering algorithm is. And so they want to say cluster proteins into groups based on activity. They have some they have some sort of drug-based activity. They have a drug screen. They apply a bunch of molecules, drug molecules against a protein, and they see some reaction, and they want to cluster them into groups based on this. And so they don't really have any good sense of what the right way to cluster is. So they are the ones who first came up with this idea of doing some kind of consensus. They didn't really formulate it. It's called ensemble clustering in bio. And then later on, the computer scientists came and said, okay, let's try to formalize these problems and think about them this way. So most of the applications of consensus are from biology, which is, to me was surprising when I first saw it. Okay. So let's move on to the next sort of important component of this whole problem of meta-clustering, right? So we said that meta-clustering, the one problem was to do exactly this, find consensus. But the other question that people have looked at is alternately called either diversity or alternate clusters. And again, it starts from the same premise. No one clustering is the right answer for your problem. But instead of saying, let me find an average answer, it's saying, let me find different answers. Let me find answers that are significantly different from each other, but also capture something interesting about the data. And again, I've given this example where we said, okay, if I have 4 blobs like this, depending on the problem we're looking at, you could think of this as representing a clustering into 4 groups. You could think of this as representing a clustering into 2 groups. Or you could think of this as representing another clustering into 2 groups, depending on which way you project, and depending on which attributes you care about. This is, of course, the simplest example of this. Everything's axis parallel, but you can imagine more generally, you have other ways of looking at subspaces where you might find answers. So, and in fact, there's a whole other area of what is called subspace clustering that says, can I find clusterings by projecting down to different subspaces? And are they all interesting? And again, the idea is that if you're looking at some subset of attributes, maybe the shape you get is different than if you look at a different subset of attributes. So there's a valid reason to be searching for alternate, distinct clusterings of a data set, rather than just trying to find one. We have, in this course, have seen a number of different tools for playing with data and doing clustering. You actually, at this point, have enough information to design pretty much every single alternate clustering algorithm that's known out there. So I don't need to tell you. You'll be able to come up with this yourself, based on what you've seen so far. Give me an algorithm to do all of that. So in other words, try to formalize the question in a way that makes sense, and then try to design a procedure. It can be a heuristic. I'm not asking for proofs. How would you do it?
Sorry, can you tell again? What's it?
So I'll make it simpler. I'll set it up even simpler. I give you a clustering. Okay, I give you a data set, I give you a clustering. I said, here's my clustering. Give me another one. That's
From
it.
the given cluster.
No. Give me another clustering of the data. That's interesting. I gave you one already. Give me another one. Give me an alternate hypothesis for what's going on with you. How might you go about it?
Well, you need to first define something.
Sure.
That's called the metric that measures the difference between the cluster.
Okay.
So
you want some way
that
to
they
measure
can-
distance between clusters?
Yeah, so that they can define what is unique difference.
So that's good because we already have an arsenal of tools of distance functions between clusters. So we have the random distance, we have the variation of information, we have a whole collection of distances now. So you can pick whichever one you want. So good, we pick a distance. So for step one, pick a notion of distance between clusters. That's why I was talking about distances last time. Because we need to have such a tool. So pick a distance between clusterings. And by the way, you don't have to go through this step. It's a convenient step. You don't have to do it. There are algorithms that don't do this step. Okay, now what? Someone? Anyone? So I picked a distance between clusterings.
I think you can get some point from one cluster, the cluster that we have, the group, and try to move it to other groups and see that the cost function decreases.
So what you're saying, it sounds like, is start from the place you are already at and do some perturbations outward from it and see what happens. Right? Okay. Step two is sort of perturb. I should call them step 1 and 2 because I think they are now giving us different ideas. So let's forget the 1 and 2. Just think of this: one idea, another idea. So perturb the given clustering. So one question I have about that idea, right? If I've done a reasonable job with my first clustering, then most likely that clustering is going to be a local optimum. Like if I ran k-means, it will be locally optimal. So any small perturbation is going to look worse. So maybe you're not surprised by that because yes, you know this was a good one. But how do you deal with that? Because most of these local perturbation things expect that if I make a small move, I'll do better and I can move in that direction. So how would you deal with that problem?
Actually, I don't like this idea to perturb.
That's okay, it's not your idea. So how would you deal with that problem?
Nothing personal.
So that in this method, when you're doing the perturbation, most likely if I've given you one clustering, it's a local optimum. So any perturbation is going to look worse. So how do you deal with that problem?
Maybe getting a bigger jump, I don't know.
Okay, but you have to somehow. I mean, you can't just say I'll look at because you just said I'll just step away. But then you have to decide, do I want to keep that new candidate or not? It's like if you do a random walk, right? Or if you do a metropolis, there's a procedure that says, should I keep this new point I moved to? So you have to have some way to decide whether you're going to keep that new point. So what are your thoughts on that?
Oh, maybe it's not such a bad idea. So maybe you can keep the cluster.
She's happy now. So.
What you can do is the following. You can measure individual clusters within the clustering that you got.
Yeah.
And you see if they are pretty compact, if you're happy with them, you
Yeah.
keep them.
Yeah.
And for the ones that you're not happy with, you just throw them out. Let's start from our. You know what I'm
Okay.
saying?
Yeah, sure. That's one possibility you could do. I don't know if do you have any suggestion on what else we could try to do? So to make a principled decision about how to decide what to go. So one way is to just jump very far, right? Is to be okay with going very far away. But then that amounts to just doing a random. So the more you're willing to jump away from your current clustering, right, the less you're actually using the original cluster, which is fine. But so in other words, what I want to point out is that you have to have some way to how to move, figure out how to move. So this was how to compare. This was how to move. We had to figure out how to move. Okay. Other thoughts on what we're going to be doing here?
Or probably making some estates based on other.
So what are the states? What is the natural state space for this problem?
The partitions that we can get from the current cluster by moving the points.
Right. So but in principle, any partition, right? You could get. Yeah. You had your hand was up, or are you going? No. Okay. No. Okay. So these two things are somewhat different from each other in some sense, right? Because or you could use this to say I want to move reasonably far away. Let's turn this problem around though. Instead of saying what would be a procedure, what do we want? Let's think of it from that point of view. What is the thing we'd like to optimize? If we want to get alternate clustering, there are, in my mind, two things we want, right? So for those who came in late, the question is, I give you a clustering, I want to find a new clustering that's somewhat different from the one I gave you, but is also interesting in some way. So what are the two things I need to be careful about here? Yeah.
Perhaps you would want a different clustering that has a comparable Rand or Jacquard index. Well, are these labeled?
Oh, so in other words, you want its quality to be good.
Right.
Okay, so let's write that down. So we want the quality to be good. What else do we want? There's one other thing that's important in this setup. Because remember, if I just want a good quality solution, I already have one, the one you just gave me. So that I'm done.
So you want a different one.
So what is different? Make it more precise.
Different, the space, where the clusters are in space is different.
So, but how do I be more precise about difference? And this should be a way to quantify difference.
Yeah.
What do I want to say?
One way could be a different number of clusters, but that's not necessarily the requirement.
But there are other ways you can think of. So, I mean, for example, if I had a distance between clusterings, I could say I want this to be far away, right? So, quality good, distance big, right? So your method would say that changing the number of clusterings is one way to encode distance. But if I gave you a distance function, then I could actually just measure it and say, okay, I know what a big number is here. I've calibrated it, and so I want that. So there are two things I want to maintain, right? I want good quality and I want far distance. I want to be far away. Right, so if you think of some kind of stylized landscape where this y-axis is quality and this is some kind of distance, my picture should be something like this, right? That I have this solution here. What I would like is this kind of solution here, right? And that's why local moves are going to be hard to make, because the local moves are going to look bad, and then you get better to go back. So you have to somehow find these other points here. So most of the methods for doing alternate clustering boil down to something like this, trying some kind of balance between a good quality but distance that's far away, right? And the easiest thing doesn't do any of this stuff, doesn't define a precise distance, and does the following. It says, well, if 2 points are clustered within one clustering, so the first method, which we'll call sort of, cannot link plus agglomerative clustering, says the following. For every pair of points, so if I have my clustering here, this is my given clustering, and I have 2 points in it. They are in the same clustering here, so I don't want them to be in the same clustering in my new solution. So I'm going to put a cannot link constraint on them. We've seen this before. You can put these cannot link constraints. I don't want them to be together. And 2 points that are not in the same clustering, same cluster, I put a must link constraint on them. And now I throw away the original clustering and say I have a new constrained clustering problem where I want a cluster satisfying all these cannot link and must link constraints. What do you think is going to happen? Do you think this will work? If I have to satisfy all these constraints.
How do you know to put constraints?
Because I've given a clustering ahead of time. I already have one clustering. So I'm saying everything that's in the same cluster in one clustering, I don't want to be in my new one, because I want to be really different. It's like saying that I look at the vector of pairwise incidences, right? If two things are together, there's a 1 and a 0, I want to complement it. That'd be as different as can possibly be, right? It's as far away, yes?
Everything or like a majority?
Why are you asking that question?
Well, I mean, just even looking at the simple example up there that you've got,
Yeah.
about half of them are going to be remaining in the same cluster, switching from looking at the projection onto the y-axis versus onto the x-axis.
Right.
So I would argue that the end results there are very significantly different clusters, even though only about half of the points in it have really changed.
Good. So what? It sounds like you're saying something about this method.
Yes.
What are you saying?
That it doesn't have to be every pair of points within a given cluster that need to change, only some subset.
Right.
And there probably could be something said about the bounds of that subset. It may be half, it may be a little bit outside.
So what is a way to? We already have seen a way to deal with that problem. To sort of not be hard in our constraints, but to kind of be more loosey. What would you do? We already have seen a method that can handle that kind of problem. That you have these constraints saying they should be together, should not be together. Which method does that for us?
With plus and minuses.
Which one is that?
Correlation.
Correlation clustering, once again. So you could imagine an alternate clustering solution that says, take your clustering, annotate with all these pluses and minuses, but do a correlation clustering on it, which then allows you to say, look, I can't satisfy all these constraints exactly, I'm just going to try and satisfy as many as I can. And that would make you happy because now you're allowing the possibility of finding this solution, even though many of the points are still in the same cluster. Right? Good. So in fact, you can call this, you can do a correlation clustering of this. There's one downside to this. One somewhat, not heavy, but somewhat downside to this. I don't know if you can see it. That correlation clustering is purely combinatorial, right? You're not looking at the actual structure of the data. You're not looking at the geometry they live in or any other kind of information. You're just looking at memberships, who's in, who's out, and trying to flip that around as much as you can. So you might end up with something that's quite deranged in its quality, but is very far away. Right? Because it's always possible to get something that's really far away. What you want is quality, and it's not clear you'll get good quality if you just focus on the correlation aspect. Right? So you have some balances with that. Okay? Another approach that people have used is to put these constraints, cannot link. So one way to do this, which is cannot link plus agglomerative clustering, is to put these links in and then do a hierarchical clustering. With the idea that, again, you don't try to satisfy these constraints in a hard way, but kind of in a soft way. You add that to your weight function when you combine things together. If you combine two things together, you're going to introduce a number of constraints that are violated, then you might not want to do that. And so this is one paper that people wrote where they just build a hierarchical model based on this. So you're combining a normal single link hack or something like that with an extra cost function, and with these cannot link constraints, you can come up with a model. It'll give you one answer. Yes?
If I remember correctly, we can put weights in correlation clustering also, right?
You can. What kind of weights would you put?
I mean, depending upon the distance, so that the geometry is kind of preserved. The disadvantage that you are telling in the correlation clustering is the geometry is not preserved. It's basically, even if the point is very near, it will mark it just either plus or minus. It doesn't care about the distance. So if you put weights on and then do the correlation clustering.
Yes, and in fact you can do that. In fact, you can do something even more. Here's what you can do. And one way of thinking about this problem is that I want to recluster the data in order to satisfy all these constraints. A second approach says, I'm going to use the cannot link and the must link constraints to change the geometry of the space. And this in spirit is a little bit closer to what you're saying. So what you do is you essentially, this is a little bit hard to explain, and it's again very fuzzy, so I don't want to spend too much time on this. But the basic idea is that you use these constraints to build this correlation matrix, use that to build a transformation of the data. In other words, you have this similarity matrix in the data. You can essentially factorize this as a linear transformation, apply that to your data, and then recluster the data. So this is a more generalized version of the correlation. So instead of just using correlations directly, use them to change the geometry. So I get this matrix, I try to factorize it, assuming I can do so, and then that gives me some kind of transformation of the space. So I get a transformation, and now I cluster. So this is my original data. This is coming from the correlation. Then I get a new data, and I cluster this new data. Okay. Yes.
It's just a very different thought because we've used it in a different context.
Yeah.
Is there something instead of competing with what you already have?
Yeah.
Can we collaborate? So
Okay.
we learn from that
Mm-hmm.
and update something. It's more like a Bayesian approach. So I look at this and look at this. This is what you have given me. I'm assuming there is some truth in what you have given,
Yeah.
but I have some doubts about this.
Yeah.
And then I come up with another clustering where I just don't discard or complete, but use
Yeah.
this to upgrade that.
So you can, and I think what you're talking about would basically be a full Bayesian version of this problem. Because what you do there is say, start off with some kind of probabilistic model that describes the space of clusterings and the prior on them. Use some inference process to come up with one clustering. But then what you also get is some kind of posterior distribution over the valid answers you can sample from. And once you sample from it, you'll get other valid answers as well with different probabilities. You may not necessarily get diversity. You'll get answers that are all, highly probable based on the probabilistic model you built up. The downside is they might still be close to each other. You might end up with clusters of things that are close. You'll have to have some way of sampling to segregate these out. So one approach that, that in similar spirit to what you're saying that we took in a paper that we wrote a while back was to do the following. So to go back to what Himanshu was asking, right? So one problem with this approach is very ad hoc. I said, I want to just go far away from what I have. But maybe there's something good in what you had to begin with. You don't want to throw everything out, just like we saw in that example there. So suppose you start off from the beginning saying there's some kind of model, some kind of probabilistic model that describes the set of valid clusterings. Let's say they're a mixture of Gaussians and they have likelihoods attached to them, and I can talk about the likelihood of a particular clustering. Then what you're going to get is, you can imagine that if you look at the space of clusterings, for each clustering, you have some kind of probability of it showing up. Right? So this gives you a distribution over the space of all possible clusterings. And now you can sample from that space. So you'll sample things that are likely to show up. That means they have high quality, just by the way you designed the process. Right? Now it might turn out that you in this, let's say this is your landscape, and you sample a bunch of points here, and then maybe you sample a few points here, then maybe you sample just a few points here, right? What do you know? So it turns out one thing you can do is then say, okay, take a lot of samples of your space, and then pick points that are far away from each other. So in other words, pick a lot of points, let's say thousands of candidate clusterings that are all have reasonable quality because of the way you sampled, and then run something like the K-center algorithm. So yeah, let's say I want K valid solutions. Let's say I want 3 valid solutions. So take any one clustering, find the one that's furthest from it based on your distance function. So maybe I pick one that's here, and then find the one that's furthest from them, and you pick one here. You're only picking from a space that's kind of reasonably good quality. So you're taking care of that case, and you pick things that are far apart from each other by the fact that you're using this 3-center algorithm, and so you'll pick things that are far. So this idea shows up in many different papers, including some that we've done and some other people have done. That you build some kind of distribution of the space, either by a random walk, for example. So in the case that Samira mentioned, you sort of do this random walk. That gives you an induced distribution, and you can use Metropolis to build a distribution where you only pick the high quality ones, sample over that space using a Markov chain, and then do the second post-processing step to find things that are far from each other.
Yeah, but for each step, you need to do a cluster.
You don't, right? Because you do local perturbation. So what you're saying is that you build a Metropolis sort of system where you make a local perturbation using Gibbs. You perturb one point from one cluster to another, and you do these random walks. And then every now and then you keep what you get. So now you get a whole collection of things. Right? So if your Markov chain is well behaved, then you will basically get a bunch of samples from the space. And if you're using the energy function or the quality function, then you're going to sample things that are high quality. Right? This is the whole, yeah.
So this distribution over all the clustering is basically like have this ability to compute this. I mean,
Well, you don't have the ability to compute it explicitly, right? It's sort of implicit. You can build a Markov chain that allows you to sample from it, approximately. So all you have is the ability to sample from that space. You don't have the ability to write it down explicitly. This is what the Bayesian inference will give you. It'll give you a description of the distribution of the space. Right? And so you're not saying that you want, the mode is the most probable one, which is the single answer. But you want a number of relatively equiprobable ones that are diverse.
so we haven't queried all the clusters.
No, you're not going to query all of them. You're just going to sample from them. And then the sampling is designed to give you high quality ones. And then you do the distance. So in other words, this procedure, which is the third way of doing things, is first sample high quality ones, either using a Bayesian approach or whatever approach you want. And then use K-center to find far away. Far away clusters. Okay. And this is, this approach is also, they're all sort of useful in the sense that they can be applied in many different settings. Again, you don't get guarantees from any of these things, but they're good heuristics to try when you want to find these alternatives. I mean, we still, I don't think, have a very satisfactory way of thinking about this regular things. So that's why this stuff is not as clear as I would like it to be. All right, any questions? About alternate clustering? Because at this point, I mean, I'm not going to say much more about meta clustering. So this is where I'm going to stop on this particular topic. Do you think this, do you find this kind of something that would be useful? What do you think about this? Most people are trained to think of one good clustering. I mean, you tell them what that you could try to find one. They usually sometimes reaction, oh yeah, that could be interesting. Or like, why would I ever want to do that? So I'm just curious what your reaction is to this whole business of consensus and meta clustering, alternate clustering. How you feel about it? Should this be in a book on clustering? Let's put it that way. Do you think it's important to be there in a book on clustering? Is it worth knowing? I see some nods. I don't see any shakes.
This exploration.
Sorry?
This exploration.
It's exploration, yeah.
Yeah, I think it's worth it. But the thing is, it cannot be so vague as as we said. I really want to know how do you do the next step. If I have a step, how do I go to the next step? You said you do a little bit of perturbation. How exactly do I do it?
Okay.
It's actually very. I don't think it's that trivial.
I can make it precise for you if you want.
Yeah, I mean.
But I don't think precision is what you're looking for.
Yeah, that's
You're
what
looking for rigor, not precision. I can give you precision.
rigor. Yeah, I'm looking for rigor.
There is none. But I can give you a precise definition of what you mean. So take a clustering. Pick a point, pick a cluster at random. Pick a point at random. So you pick this point. Pick another clustering at random to move it to, move it there. Evaluate the cost of the new clustering. So I have the old cost and I have the new cost. Then run some kind of metropolis step minus some scale factor times E minus E prime. And then decide whether to accept the new clustering or not.
And what's the reasoning that this would give us?
The reasoning is that,
exploration.
so there is a basic result, right, in Metropolis Hastings, that if you do this kind of sampling, in the limit, if you mix sufficiently well, you will in fact be sampling where the probability of picking a particular clustering is proportional to the energy.
Yeah.
And if the energy is your quality measure, then with higher probability, you will pick higher quality clusters. That's the rationale behind this.
Yeah. Okay. So now I understand what you're trying to say.
Yeah.
So you're trying to connect the sampling theory with the clustering.
That's right.
So how do you do this thing? It doesn't matter as long as you satisfy.
That's right. And so if you, for example, if you had a Bayesian model, then
Yeah.
you could infer some kind of posterior distribution over good clusterings, and usually in these Bayesian settings, you are able to sample from the posterior, or there are ways to sample from the posterior using essentially MCMC methods, even if you can't actually write it down. So the hope is that you have some way of sampling from the distribution you want to search for, and then you do that.
I think it's good. Can you tell more about the distribution itself?
The distribution itself, what do you
Yeah.
mean?
What's the shape? The shape? What's
It's
the
highly
form?
non-convex. I don't know.
Yeah.
I mean, yeah, it's very, very bumpy, right? I mean,
So like because when you're mixing, when you're doing this sampling, there are these mixing parameters and all
Yeah.
those things. So they're like
again, these are heuristics. I mean, you need to talk to an MCMC expert for this kind of thing. But usually, I mean, in practice, these things,
yeah, you're trying.
You run
That's what-
them. They do a bit of burn-in, and you try them for a while, and you do what you can. It's a good point though. I can't guarantee for you that I have good coverage of the space, and that's why these are only heuristics. I don't really have a good sense of that. I don't know how long it will take to mix to get to that desired solution. These are not easy things to argue about. So that's why these are heuristic methods. So you try them, you see what works. But in practice, they do tend to give you good diverse answers. So like at least I can say for the work we did when you did this, you were able to get answers that you could actually interpret. Oh, you're clustering by faces, you're clustering by the shadow, you're clustering by the orientation, and I'm getting different clusterings that have meaning, semantic meaning to them by doing this thing. But I can't say this would be true for all data sets, for all methods.
Sure.
But this idea keeps one test of a good idea is that people keep reinventing it without realizing it. And so this basic idea of trying to sample and do diversity after sampling shows up in different contexts.
So basically, this generalizes the clustering problem, right? So we said before we were given a point and we want, let's say, hard
Yes,
clustering. Right?
yes.
Or we're given a point and we want hierarchical clustering.
Yes.
But now we're given a point and we want a distribution over the clustering. Sort of.
Yes.
So.
Yes. Although it's phrased that way, it's just a Bayesian problem. But this is more like I want a collection of clusterings that are. But the distinctness I think is important here. It's not just enough to have a distribution. I want them to be different from each other.
Yeah, yeah.
That's the issue.
That's what
Yeah.
You said it doesn't have rigor. What kind of rigor do you want to see in this?
I would like to say that if I ran this procedure, I can guarantee that I will find a clustering of quality that is comparable to the one I gave you in some measure of comparability, and is at least so much far away after running for a certain number of steps.
So you want to have that prediction before you run that.
Yes. So
Some
for example,
kind of limit or something.
like for example, when I talked about k-means or k-median, I said, oh, if I do this initialization, I can prove that it will converge in so many steps, and the answer I get has so much quality.
Okay. Because dealing with data, everything is ad hoc. You.
Yes, that's true, and clustering is a particularly good example of this. But as we've seen in class, right, there are many cases where you can take an algorithm that looks heuristic, you can modify it, and give some guarantees for things like spectral clustering, for correlation clustering, for hierarchical clustering, for k-means, k-median, k-beta. You can give guarantees for these things. So I don't think we should feel like we have to give up on that possibility. Right now, we don't have an answer. But that's I'm always, at least my personal philosophy is I always want to see that I can say something formal about what we have, because that's a guarantee. No data will ever change a guarantee.
Because
It's
there's always
counted.
a trade-off. Like whenever you give guarantee, you have to make questionable assumptions.
No, why?
Like
Why?
with Bayesian or the standard frequent is like they give guarantee about the bounds and all those things,
Yes.
but you are making assumptions about.
It depends on the theorem. So at least for algorithms work, when you give a bound on, say, the running time of an algorithm or what quality it gives you, there are no assumptions. Zero. Or conversely, even if you give a bound with assumptions, at least you made them explicit. Because the assumptions are telling you, essentially, if your data looks like this method will work. So the actual act of proving a result of that kind basically says that this algorithm is capturing this kind of structured data. If you don't have a structure, don't use this algorithm. Go look somewhere else. So the results of that kind, the guarantees, give you a kind of a map. Right? They may not always give you what you want, but they give you a map of what to use when. And I think that's also important. Okay, any other questions before we move on?
There's a paper by Benjo about deep learning and exactly this sampling. So, and what it's not rigorous in any way written, but the idea is like this: when you learn these multiple representations, right, multi-level representation, you're actually capturing higher and higher level of representations, and as such, the entropy of the data is increasing. If you imagine at the lower level, you have extremely bound,
The data is the same though.
no, the data is not the same because they have different representations.
The representation has changed?
Yeah, the representations have.
So the representation has a different entropy, not the data.
Sorry.
The representation.
The representation of the entropy has changed. Yes. So you have.
Sorry. So.
Okay, so if you can imagine at the beginning you have like this really bumpy landscape, and it's very difficult to sample from and to move around, to navigate. But then the higher you go, it turns out that these representations, as I said, they're semantically they represent a higher level concept, and the entropy of the data, these distributions become nicer, easier to sample for, easier to move on. And as it turns out that you can sample on the top level of hierarchy, or top level representation, relatively easy. Let's say use some MCMC, which is because the entropy increased, it's easier to sample from. Then you propagate this down to the original data, because you have the entire path on the multiple levels. You come down to the original distribution, and you can take a sample from there.
Okay.
So in other words, if you imagine that you have one distribution that's really ugly, you have multiple transformations.
Yeah, fine. Okay, so what's the point?
The point is, I'm just saying that, this is also one. I'm just saying that this is one way of thinking,
Sure.
of clustering.
So I mean, any hierarchical model for data has the property you just described.
Yes.
It's not just a neural net. Anything has that.
Yes, yeah, you're right.
Right. So if you have some hierarchical model, as I said, if you have a probabilistic model for your data, you can think about sampling process in a more rigorous way. That's what I'm trying to say. It has nothing to do with.
Yeah, that's true.
All right. So let's move on. I think we're moving on from meta clustering now. I want to talk about another topic that has in recent years generated some interesting controversy and discussion in the clustering community at large. And this is this whole business of axiomatization of clustering. And this is one of those topics where I think it's, again, like with many things, there's no right answer. So I'm really interested in hearing your thoughts and opinions on what you think of this. This is not those things where I'm just going to tell you stuff and you should just learn it. This is more of an argument we should be having about whether this makes sense or not. One of the things that has sort of plagued the whole area of clustering is this sense of that you can't, there's a sense of ad hocness that you can't really get away from. There's at some level, you're just making random choices about things and you're doing stuff, and that seems reasonable, but there's no principled way to argue that what we're doing is the right way to do something. And so in that line, the effort, the axiomatization effort basically says, can we come up with some set of axioms that capture what would be considered a good cluster, as opposed to just an arbitrary partition of data? If we could do that, and we could agree that these axioms characterize what good clusterings are, we might be able to say, okay, let's look at any clustering algorithm that satisfies these axioms, then by definition will give us a good cluster. And this takes away all the issues of, is this a good answer? So the attempt, and this was by a researcher called John Kleinberg, who's at Cornell, was an attempt to understand, in other words, so if you look at the space of all partitions of a set, right? Not all partitions are going to be what you'd consider a good clustering of the data. Right? Some of them will be crappy, some of them will be decent. Is there a way to sort of divide this into, the good stuff and bad based on adherence to certain axioms? It's like how you can define Euclidean space by a set of axioms, you can define hyperbolic space by dropping all these axioms. So can you sort of axiomatize this space? And so he came up with this paper that was quite interesting, that proposed a couple of axioms, and then showed that no clustering algorithm can satisfy all of them. So this is kind of like if you ever, how many of you have heard of Arrow's theorem? What democracy is a failure? Oh, not crazy. So Arrow's theorem is this very beautiful result in social choice theory that basically lays out a reasonable set of axioms you'd want for any election system, and then shows that no election system can satisfy all these things. So every election is doomed to failure. There's been a lot of work since then, but this and other things is what got the Nobel Prize in economics many years ago. It's a very nice result. But this, in the same line, he showed this impossibility result, saying that I'll give you some axioms for what would be considered reasonable for clustering, and then I will show that no clustering algorithm can satisfy all these axioms. And of course, a result like this is only as good as the axioms, right? There's no point saying this result is a good result or a bad result unless you look what the axioms tell you. The axioms tell you silly things, and you'll get silly answers. So on that note, let me write down the axioms. We'll see what we think. Okay. Axiom 1 is what we'll call scale invariance. And before I do that, let me make sure there are some subtleties in exactly how the thing that you're axiomatizing over. So let me be very clear about that. Okay, good. So before I give you the axiom, the object of interest here is going to be a function. The function is going to take an input x and is going to output a cluster. In other words, some element of the partition space of x. The axioms are about such functions. Right? We have the space of all possible functions, and we're going to try to reason about what makes such a function good or bad. Okay? We will want these axioms to say that a function satisfying these axioms will give you good clusterings. A function not satisfying these axioms will give you bad clusterings. Okay? Keep that in mind. All right. So the first property we have. So let's assume that there's the space admits actually some distance function. Okay? It has some structure to it. It's not arbitrary space. Otherwise, it'll be very hard to. So the scale invariance property says that. So if so let's say there's some given for, actually let me be a bit more careful, for any distance d and some alpha parameter, some scalar, then the output produced by the function on the input x and d is the same as the output produced by the function on xn alpha times t. Your glasses?
At least glasses for you.
Okay, so before we, let's try to understand what this is saying. What it's saying is that if I take my data, and they have some distance to them, I just blow up everything. Okay, make everything bigger by a factor of 2. Then so I take my data, run my clustering function on it, get some answer. I take everything, blow it by a factor of 2, run my same clustering function and get another answer. They should be the same answer. The same partition of, so if 2 points were in one cluster before, they should be the same cluster later. What do you think about this axiom?
There's no sense depending on the x.
Sorry?
This makes sense, but depends what the x is.
What do you mean? X is the.
Let's say if x is Euclidean space, I think this is okay.
You mean D? D is a distance function.
Yeah.
Depends on D. So D's Euclidean space is okay.
Yeah.
Why is this okay?
Because this, the transformation of distance having twice as much distance is kind of natural for us. If you
Why
say
is it
that-
natural?
If I have 2 points at the distance x,
Yeah.
and then I take them 2 times away, then it's it scales nicely. I mean,
Why?
it's-
You're just saying nicely. You're saying it's good. You're not giving any. You're just going in circles. What is nice? What is good?
it means that everything is within the sphere of 2D.
They're within the sphere. But if I scale, they're not anymore.
Yeah, then it's going to be 2D. So if you scale it or alpha D.
Okay. So anyway, think about this. I mean, it seems. I'm willing to concede that it seems plausible. I'm not willing to concede that it's obviously right, and neither should any of you. It's an axiom. I'm just saying this should be true. The best way is to test out algorithms you've already seen and see if this works. Yes.
But so from a mathematical perspective, scaling is nice, but it's really unnatural in another setting.
Do tell.
Well, no, if you just look in biology, you just can't scale things. So there's a really famous set of expository articles about how you couldn't scale a gorilla to get King Kong.
That's right, because the things scale at different rates. The skin scales as square, the volume scales as cubes, and things just get messed up, right?
So and as far as helping with real-world data, I don't know if this is even desirable, if possible.
Okay, good. So we have some feeling that this is reasonable, some feeling of skepticism. And as you're both saying, this depends on the domain you're working in, right? For the domains that we've seen so far, Euclidean spaces, vector spaces, this would seem reasonable. But maybe there's a domain where it's not reasonable. Okay, good. Axiom 2. We'll call this richness. That the range of f is equal to. In other words, it's possible to achieve any partition for the right input. What do you think about this section?
I don't think this axiom tells you a lot, actually.
No?
No.
Okay. Anyone else? Maybe your question is, why on earth do we need this in the first place?
Is it?
Why might this be a good thing to have? Or rather, what would happen if this were not true?
I mean,
Your f would be biased.
Well,
it tells me that the algorithm is flexible in the sense it can cluster and you give me any data points and I can cluster and can achieve what is optimal, because optimal can be anything, right?
that's basically it. That it's saying that the method you have, the f, is expressive enough to capture the entire space if it needs to.
Right.
That is not fundamentally limited. Right? You could imagine a clustering algorithm that puts everything in one bucket. Okay, it's dumb. It violates richness, but it might satisfy other things. It's scale invariant for sure. And so you want your clustering method to be expressive enough, to not be limited, to not be biased in some way. And so this tries to capture that. So it's in some sense a negative axiom, right? If it's true, yeah, whatever. But if it's not true, then bad things are going to happen. This last one is a little bit more involved. Yes?
Is this the killing axiom? I think none of the methods that we had so far are so expensive.
We'll have to find out. Won't we? Okay. So let me to define the third axiom, which I'm going to call consistency, or which I'm going to keep on consistency. I have to do a bit more work. It's a little bit. It's not as elegant to write down. And the axiom. So let me first define a notion of a transformation of the distance function. Okay. Okay. Well, let me say this one. So let's say I've given two different distance functions on X. Okay. And let's say I'm given a cluster, some particular clustering, which belongs to the partition space of X. Okay. And let's say the following properties hold. So this is a clustering, right? So if ij in the same cluster, then d prime ij is less than or equal to dij. That's property 1. Property 2 is if ij not in the same cluster, then d prime ij is greater than or equal to dij. Okay? Suppose this property holds. We will say that then d prime is a transformation of d. So before we go any further, let's just talk about what we're saying. What we're saying is, suppose we take the transformation is doing the following. For things that are within a cluster, it's kind of shrinking them together. For things that are in different clusters, it's putting them far apart. Okay? The consistency claim, the axiom, so this is the definition of a D transformation. So the consistency axiom says, if f of x comma d is equal to some partition gamma, right? And then d prime is a transformation of d, then f of x d prime is also. What this axiom is saying is that if you take a clustering, take points that are in a cluster and shrink them to each other, closer to each other. Take points that are in different clusters and make them further apart. Your partition should not change. So in other words, if I had one clustering that looked like this, so this is one blob here, this is one blob here, this is one blob here. If in my new clustering, I took this and I kind of shrunk these so they were here, I shrunk these so they were here, and I shrunk these over here and I pulled them further apart, the output of my algorithm should not change. Of my f. My f should give me the same partitioning of this as it did of this. And of course I've drawn this example so it should do that. That seems like a reasonable thing to do. These are the three axioms that Kleinberg proposed are satisfied, or should be satisfied, by a reasonable clustering algorithm. And then he showed, so his main result is that no clustering algorithm, no f satisfies all three. Yeah.
So these should be satisfied on any given set of points.
Yeah. Well, it's a property of the function, not of the data.
No.
Because the function is defined as a mapping
Right.
from.
Right. Yes, that means all the points.
Yeah. And he also helpfully pointed out examples of clustering, actual real clustering algorithms that satisfy every two of these three. So it's not as if these things are coming out of, so his argument is that these are not coming out of nowhere. If you look at actual clustering methods, they actually satisfy two of these three methods. So for example, suppose you do a single link hierarchical clustering. Okay? You say, I'm going to use this to find a k clustering of my data. Okay? So by merging. Does it satisfy scale invariance? What do you think? So remember how single link hack works. You take the points, you look at the closest pair, merge them together, you take the next closest, merge them together, merge them together. Keep doing this till you have only k clusters left. Would it satisfy scale invariance? What do you think? Would it, if I took every distance in my space and multiplied it by 2, do you think the algorithm would change at all? So run single link hack in your head with all distances multiplied by 2. Do you think at every step of the way, you can look at what the algorithm is going to do compared to what it would have done before? Do you see any differences? Any thoughts? You're frowning, Shaz. Any thoughts?
It should work.
Huh?
It should work.
Can you explain more about that? So give me this binary answer.
The closest pair will be closest even after scaling.
Sorry?
The closest pair will be
The same. Because everything's scaled by the same factor. So whatever's closest before will be closest next. So you take that pair. Now again, whatever's closest before will be closest again now, because everything's scaled by the same factor. So it shouldn't be too hard to run this in your head and say, okay, this is going to satisfy scale invariance. It's not that easy to tell, but it will also satisfy consistency. That if you shrink all the points that are close to each other and shrink the pull away points that are far apart, it'll still, you had a question?
Okay, so what about complete link hack though? Given that fundamentally the
But I'll get to complete hack.
Okay.
Let's finish the thought process around single link hack, and we'll get to complete hack. Right. So with a bit more work, you can convince yourself to satisfy consistency as well. Will it satisfy richness? So let me repeat very carefully what I'm going to do. I'm going to take my algorithm, I'm going to run it, and I'm going to stop when I have k clusters. Does it satisfy richness? Can I get any partition using single link hack? Can I get a partition with k minus 1 clusters in particular? By definition, I can't, because I said I stop with k clusters. So k means, k median, single link hack with k clusters do not satisfy richness, because you can't get an arbitrary number of clusters. With something like correlation clustering, you could get an arbitrary number of clusters, but you can't do that with any of these methods. So they just fail on the richness count already. Now let's come to your point about complete hack.
all right, so complete link tends to bias and pull in outliers.
Yeah.
Um,
So it
do
should
not
satisfy
look-
scale invariance, I would bet.
Does that outliers?
Well, because everything is scaled by the same factor, everything that was an outlier before is an outlier now. Everything that's close is close. So I don't think scale invariance will be a problem.
Okay.
I'd have to think more about consistency. I'm not sure. It would also have the same problem with richness if you stopped at some point.
Right.
Yeah. Right. So richness is a somewhat artificial constraint, as you can see, because you could any method that fixes k is going to fail the richness test. So you can only look at methods that don't fail the richness test. So think about things more.
Yeah, so is there a clustering algorithm that satisfies exactly one? of these
Exactly
problems?
one.
Yeah, not 2 out of 3. And a good one, not like, just a
Right, because I could satisfy this by just collapsing everything to 1 point.
Yeah.
It satisfies exactly scale invariance. It does not satisfy richness or consistency.
Not something bad, like something natural. Like,
Is there a natural clustering algorithm that satisfies
or by
exactly?
natural, just something good that, arguably.
Yeah, that people have
so-
thought of before. Like that. That's a very good question. I'm not sure I can think off the top of my head. What would be a candidate? So I would like to say, this is a bit unfair because this is a very specialized topic that I don't know about, that if you're trying to do, say, k-means clustering on a collection of distributions, it would satisfy consistency It would not satisfy richness because of the K. It would not satisfy scale invariance because you can't scale distributions. They're not scale invariant. The natural Kullback-Leibler divergence, for example, on distributions is not scale invariant because you're on a simplex which is bounded. You can't do it. So that would be my candidate for a method that satisfies only one of the three clustering distributions. But I'm not sure. It's a good question. So yeah, so he basically showed that there's no function satisfying all these three axioms. In particular, he showed the following, that if you have a function that satisfies this and this, it can never produce two nested clusters. It can never, okay, so again, go back to the lattice, right? So in the lattice, we talked about the split merge operations. You're clustering here, you merge some sets and you got another one here. Okay, so again, using the language of partial orders, a chain is a sequence of things that form an order among them. An anti-chain is a collection of things that have no ordering relationship among them. Okay? You're going to show that, or at least she showed that satisfying axiom, any clustering algorithm, satisfying axioms A1 and A3, like the ones we've seen so far, the output will be an anti-chain. You can't have two things that are nested, and therefore it cannot be rich. That's basically the proof. That anything that satisfies these two cannot satisfy this as well. That's why all these methods that like K-medians cannot satisfy this because they're limited. They have this anti-chain property. Because they have only K clusters. So he proved a more general version of that. So this paper, generated a lot of controversy. Mainly, first of all, because he was saying that it sounded like he was saying clustering is impossible. Right? Which he wasn't quite, but that's what it sounded like he was saying. And also because people started arguing very vociferously about these axioms. So I would like to think, at least for the next few minutes that we have, about how we would argue against each of these axioms a little bit. I have my own thoughts on this, but that's just me. So we've talked a little bit about scale invariance. I think we mentioned that there are arguments where scale invariance doesn't make a lot of sense. And I can give you a specific example of this. Basically, again, if you're talking about clustering distributions tend to live. Remember, if you think of a distribution of a finite domain, it's a collection of probabilities, P1 up to Pk, such that sigma Pi is equal to 1, right? So you can actually imagine this as living on this thing called a simplex. So I'm going to draw the simplex in three things. Right, so this is the triangle here, because it's the sum of things that sum to 1. And so you can't scale this, right, because this has to be fixed. Any scaling would change this number. You're not allowed to scale. So if you're living on a distribution space, you no longer have scale invariance. You can't, doesn't make sense to scale this. So that's one way to destroy this. I'm not sure how you would argue this is irrelevant. I'm happy to hear thoughts on this, but this is not a good axiom to have. I mean, one thought just came to mind right now while we're talking. I don't know.
I mean,
why for probability?
One second.
in general, I mean, if it's very expressive, I mean, maybe that's just not useful in practice. You know what I mean?
Can you think of an example where that is true?
Yeah. Well, I'm thinking about we're doing machine learning. Really, that the more expressive. So if you have too expressive of a class, there's a higher chance of overfitting.
Ah, interesting. So you're talking about things like VC dimension and stuff, right? That's stuff that Vivek was talking about, like the pack learning realm. That if your class is too expressive, you want to limit your class size to prevent overfitting.
Or just like with decision trees, for example, you might just want to stop them at a certain height.
But this is a very good observation. I didn't think about this. So the argument here is that richness can be a bad thing if it makes your class of clustering functions too expressive, and that could lead to overfitting. I like that. I should remember that one. Okay. Very good. You were saying, Clement? You had a thought?
This is about the probability of scale invariance. The sum of p's doesn't need to be 1. It can be d alpha 1.
How do you interpret them as?
The same. You just take the relative of that anyway. The ratio.
But suppose now you're clustering them, and what you have is this as your distance function. Kullback-Leibler divergence, which is the natural information theoretic distance function. Now what? That doesn't scale. In fact, it's particularly bad. What happens is that as things go further out, things get squashed. There's these Bregman divergences, they behave very badly as you sort of scale out.
Yeah, but you can, what I'm saying is of any numbers, right? If you can have a sequence of numbers, you can convert it to the probability distribution.
I know that, but what I'm talking about is not that. I'm talking about what you do with the distance function. The distance function behaves badly because it's non-linear. It's not translation invariant. The distance between 2 points here is not the same as the distance between 2 points here. It shrinks. For many of these Bregman divergences, the distances shrink because your Bregman divergence is defined by this measure, and as you go further out, it kind of changes. It actually blows up, sorry, it becomes bigger. So it's like hyperbolic space. Things kind of go out and go crazy. I mean, and a hyperbolic space is another example where if you try to cluster things in a hyperbolic space, the distance as you move out, it's not translation invariant. Things just blow up. And so there's this. What about this one? This weird consistency axiom. If you had to pick this apart, what would you be saying? So it's saying something that sounds very plausible. That if you make close things closer and far things further, it should not affect anything you do. Your clustering algorithm should be doing the same thing as it did before. It should not be doing anything different. That, at least to me, sounds extremely plausible. I will say that for a long time, I couldn't quite figure out why I should be worried about the consistency axiom, even though it seems so complicated. It seems very reasonable. So here's an example that another paper sort of talked about that shows why you could make a change that's consistent, but your answer might want to change. So suppose I have a clustering. This picture here. This is my clustering blob. There's one blob here, one blob here. I don't think it matters too much where they are, but these are my clustering blobs. Okay? So there's lots of points inside them. Let's call them 1, 2, 3, 4, 5, 6 clusters. And here's a transformation I'm going to do. I'm going to keep these guys where they are. Okay? Now, I want to make sure that things that are different clusters move apart. So I'm going to take that, I'm going to send it out here. Okay? And then I'm going to take this 5 and also move it there, but not move it too close. So it still stays further, at least as far apart as it was before. And I'm going to take the 6 and move it out here. Okay? This is a consistent change by the definition of consistency. Things within the same cluster are staying together. I've not changed that. Things that are different clusters are getting further apart. And while you can argue that this original clustering is still a valid clustering here, you might also be willing to argue that this clustering is actually a better one. Right? That in some sense now, even though the individual clusters are still valid, there's something better you could be doing. And your function should take that into account if it's trying to do a good job. And it turns out there was a follow-up paper, which is quite interesting, that said that one of the problems with this Axiom system is that it should have been reasoning not about the clustering that you produce, but about the cost of the clustering that you produce. That if you do scale invariance, the cost should scale. If you have richness, richness is fine, you can leave it the way it is. And if you have consistency, that the cost should not change. And that's going to be true here. If you move this, the cost will not go up of the original clustering you had. It just may no longer be a good one. And so they said that as long as you change your definition of the function from measuring the clustering itself, but to measuring the cost of the clustering, then these axioms are in fact consistent with each other. You don't get this contradiction. It's only when you worry about the actual object you produce that you get to know these problems. And this is maybe a topic for a different lecture, but this distinction in clustering between the cost of the answer and the answer itself is something that bedevils the field, that people are trying to deal with. That just by changing the cost by a little bit, you might get a very different answer. Or by changing the clustering by a little bit, you might get a very different cost. And these two things are not exactly the same as each other. In some cases, you want to know what the cost is. In some cases, you want to know what the answer is. And depending on that, you might choose a different method. All right, so the world is divided into two kinds of people: those who like axiom systems and those who don't. I'm in the category that does not like axiom systems, so I'm not going to talk about this much more. But I thought it's interesting to see that people have actually tried to think more sort of in a principled way about how to reason about clusterings. And so far, again, we don't have very good answers, but there's some interesting insights have come out of this effort. Okay, all right. So I'll see you all after spring break.